Okay, hey everyone. I can barely see you, but we're super excited to be here. And today we're going to talk about physics-driven UIs in your Flutter apps. This is Jesper, I'm Tim, and let's dive right in. So in June this year, something happened that probably all of you heard about. Apple announced a comprehensive new redesign of their platforms called Liquid Glass. And it might be the most complex design system that was ever deployed at scale. Just to get a gauge for how everyone feels, who here has like a general positive feeling about liquid glass? Okay, okay. Who's neutral about it? Who doesn't really care? Why are you here? Uh, and who feels negatively about it? Okay, yeah, that kind of fits, honestly, what we were going to say. It was quite controversial, so it triggered a lot of emotions. People were wondering if it's something that Flutter could handle. People were saying Steve Jobs would have fired everyone. Um, so yeah, it is a controversial thing, and today we want to start off by talking a little bit how we even got to this point.
So, I was told before I was born, computers actually always looked like that. We still use that. CLI command interfaces are super powerful, but they have one problem: they are super abstract. So the user has to learn a specific syntax to do easy tasks like making a note, right? And the problem is the whole interaction with the system is purely cognitive, and there is no visual or tactile support that you get from the system. So this era really sets the stage for what's missing, basically, and this is a system that also my mom could operate.
And that changed in the late 70s and 80s with a couple of key innovations. Most of them happened at Xerox PARC. And one of them was the mouse. So people could now start interacting with the interfaces directly. And that ushered in an era of metaphors where suddenly we have a trash can on screen and a clock and a calculator. And this enabled people to directly interact with things they are familiar with from the real world for the first time.
So, and then in the coming decades, we basically pushed that to 11, right? Designers used more and more icons and textures to make systems even more visual and nice. Um, the computing power grew also over time, and this is how we enabled more complex physical-based animations. And they also are really popular on mobile end devices. One early example is Cover Slide on iPhone. And yeah, by adopting GPU acceleration for the graphical user interfaces, we basically could pull this off without slowing down the main thread too much. And yeah, that's where we are.
And then in the 2010s, we shifted gears again. And this started actually with Windows Phone, but then iOS 7 got more popular. So most of you probably remember that. And this new flat design language stripped away all the shadows, all the textures, and went back to basics, basically, and communicated hierarchy with colors and spacings again. However, designers still needed to find a way to communicate depth because they stripped away shadows in most places. So they came up with new ways. For example, in Windows Phone, you can see it in the video, there's this parallax effect when it's scrolled to the right. And on iOS, we had also a parallax of the wallpaper, but then also blur effect became really popular at that time. And the key thing to note here is that is compared to shadows, this is a dynamic effect that is calculated from the GPU dynamically. Oh yeah, and then that trend also extended to all kinds of interfaces.
All right. So the question is a bit what's next, and one big trend of the current time is VR and AR. And if we create an AR interface, we want that our UI lives in the world of the user. And in order to connect that virtual world and the real world, our UI elements need to adhere to some physical rules, otherwise it feels disconnected. And you could see here the picture frame, for example, it casts a shadow on a real object, and this is how the picture frame gets integrated into the real world. And this influence then basically was carried over into UI, 2D UI again.
So yeah, we basically started to combine both of those design languages. You can see the dynamic island on the left. There's a bunch of shadow effects again. There's reflections on this card. Also, the dynamic island itself moves like a liquid. And then Microsoft also used this type of materials and shadows a lot in their promo videos. It never somehow ended up in their UIs, but they acted like it would. And on the right, we also have another example with the Arc mobile browser where the page folds up like a paper. So we are now in kind of this in-between phase where things with abstract meaning are combined with these realistic metaphors again.
All right, so if we zoom out a little bit, we could say, okay, our designs are becoming just more and more dynamic. There is Material U, which introduced this personalization through color schemes, where the user could pick a wallpaper, for example, and the whole system adapted to it. And it did it in a smart way so that still the contrast and the accessibility were maintained. And Liquid Glass actually works similarly, right? They try to put the user's content at center stage, and in order to do that, they have glass. But to maintain contrast and accessibility, again, they also need to have dynamic glass, right? So it adapts its shade, for example, based on the color which is underneath. So yeah, I think we have a clear trend now, right? We get more and more compute, and this makes our HMIs more and more physical.
So that is what Apple wants you to think, but actually the trend isn't quite as clear as we are making it out to be. We're lying to you a little bit. So if you look back into the past, you see a lot of user interfaces like Arrow in Windows Vista was the first one to introduce dynamic blurs. And physically based motion was on at least people's hands since the iPhone 1. Also, early desktop environments experimented a lot with physical motion and shadows. You have these jiggly windows on GNOME desktops, but also on the right, I don't know if anyone remembers this, but it was called Bump Top, and it was like a four-wall desktop. So it's not quite as clear.
Yeah, so where are we now? So what is actually guiding our designs? And I mean, at least in our opinion, there are a lot of forces. So we have UX pulling on the design, there is accessibility, there is the need to create something novel, there are design trends which are also swing like a pendulum and come and go. And then there's corporate identity. So we try to maintain a certain look and feel to our products so that users can recognize them. So we would argue that design in the end is actually a compromise of many forces.
So what we want to do today is to basically cut through the weeds a little bit for you and talk about the things that we think are actually valuable from these trends and that you can use in your UIs and that are here to stay, that are not just part of a trend necessarily. And we would like to start with surfaces. So what are surfaces? It's not like a set definition, but we are basically saying every UI element is a surface. So you have a surface to interact with. And the first treatment you can give it is a color, very simple. You can give it a shape, and you can give it a texture. And if you compare that to the surface we started out with, obviously you all see it jumps out at you a little bit more. It creates a hierarchy just from these three things.
All right, and the next step is you take your surface and you need to place it somewhere in your app, right? And placing is actually difficult, but it works really well if you just shine some light on the surface. So it creates some shadow, and the shadow is actually placing your surface in your app. You can also add some gradient. In this kind, we basically just simulate some light that shines onto the object. And then we can add a border which acts like a specular highlight on our surface. And if you compare this again, it already looks way more physical, right? The right one feels like you can touch it, and the left one feels more like a dead surface.
So if you think about those things in unison, what we are basically creating here is a material. So materials in the world are defined by their surface texture and the way they interact with light. And taking this concept further, you can create all kinds of different surfaces if you want, inspired from the real world. You can create this holographic shader. You can create a liquid metal surface that you can interact with. Or the thing in the title, you can create glass if you take it to the extreme, basically.
So if we want to summarize this, what we can do with surfaces in order to achieve goals in UX, one thing is create affordances. So we can teach the user about what surfaces are tappable, what surfaces are disabled right now. But we can also establish depth and space, for example, through shadows. And we can direct the attention. I mean, you all know the floating action button, and this one is floating because it's normally the call to action, and it is more important than the other parts of your app, so it's floating above them. And the last thing is communicate state and feedback. So, for example, you can clearly see that I press the surface by the surface treatment that we give to the surface, and this is a pressed state, and this is a tappable state.
So let's talk about how we do this in Flutter. It starts pretty simple. You start with a colored box. Who here has built a colored box before? Yeah, you don't need to, I think. So yeah, it's just a box decoration. The key thing here to notice is like rounded corners. Of course, they're meant as like fun modern treatment, but also in the real world, no corner is perfectly sharp. So it makes sense to round your corners a little bit if you want your UI to feel more physical. If you want to add a gradient for lighting, you can do that as well with a foreground decoration. Probably also most people know this. And then you have a gradient that shines on your object.
So if you continue with the same idea, we would add now also some noise texture. So you can do this in the foreground decoration where you just add an image, so it's paint on top of your children. And then you can blend this with a blend mode and a color into your widget. So the next thing is to add a shadow. And I mean, you all know how to add a shadow. There are two tricks that you might not know. You should use at least two shadows. One is the more ambient lighting, and one is a so-called contact shadow. And this simulates just better the reality of shadows. The other thing is you can treat your shadow with a little bit of color, and this gives an effect of global illumination, where basically a surface scatters the light and shines it back onto the environment where it's located. And if you are lazy as I am and you don't want to think about this all the time, you can use a widget like physical shape, which basically handles some of these ideas already for you. This is basically the template for most of the material widgets that use elevation.
If you want to go a step further and you want a more custom surface and interaction, you can use Custom Painter. So in this case, for example, we want to have the surface that feels a little bit alive. There is a moving gradient that could represent some sort of AI thinking state. And that is actually also quite simple to achieve with Custom Painter. In this case, we just paint a bunch of radial gradients at the bottom of the screen with a blur and a specific blend mode. And we also have a noise texture overlay that you can't really see on the projector probably. But who here has ever used Custom Painter actually? That would interest me. Okay, that's also quite a lot. Cool. If you want to take it even further, you can use a render object. And that basically, for you, it does what the Custom Painter does. But on top of having access to the canvas, you have access to the child's layout, as well as painting the child. And in this case, we have this magnifier, which needs the child's size to position the magnifier, and then also is able, through engine layers, to paint a scaled version of the child that is clipped to a circle. So we end up with this. And who here has written a custom render object before? Okay, that's already much fewer people. So we don't have time to go into this deeper, but we're going to link to another talk from this year that went into exactly these details at the end of our slides. And then if you need access to the GPU, obviously you have fragment shaders. And this is actually Liquid Glass. Our implementation is built with a combination of all these things. But a fragment shader, the biggest advantage is you get access to each pixel of your child. So if we go through this real quick, we can load a fragment shader, which is basically just a GLSL file. And then you have two options to use it, basically. It's an animated sampler that comes from the Flutter shaders package. What that does is it basically takes a screenshot, so to say, of your child every frame, and then you get access to that screenshot in a callback, and you can pass it into your shader and paint it on the canvas. This is actually wrong, I'm sorry. We would paint this shader onto the canvas instead of returning a child. If you're on Impeller, it's way more convenient now. You have access to a constructor called imageFilter.shader, and you can just pass your fragment shader in there, and then it does all the setup for you. And that's just saving you code, but the actual cool part is you can pass it into a backdrop filter. So instead of modifying the child you want to build, you can modify everything that is behind the child. And that is really powerful because it enables an effect like liquid glass that distorts all the elements behind the object. And here at the end, we have a little bit of pseudocode for how a shader would look like. You have input uniforms, and then you modify pixels one by one, but also this is not entirely what this talk is about. So if you want to learn more about that, we have resources at the end.
All right, that basically concludes the part about surfaces. So we now know all about surfaces. The next part is about audio and haptics, and we dive into audio first. So in UX, audio has normally like 3 roles. And the first one is a so-called sonic identity. You recognize the brand, right? So it works. The next one is passive sounds, and this is when your system calls for attention. Also pretty clear, I think. And for physicality, the last group is the most interesting one. It's active sounds. And one is that it amplifies the meaning of the thing that just happened while you interacted with the system. I think it works. And the other thing is amplify physicality. So if you interact with the system, you try to do some interactions, and then actually sound can help to make the interaction more physical. And this is what we want to look into now. So when the box falls down, what we want to hear is some reaction with the surface. And normally we hear this as a sound and or as a haptic feedback. And one super public UI element that basically employs both is the date picker from iOS, and you all know it, right? It makes the click sound, and it also plays the haptic feedback, and this is how it pretends to be a physical object, which actually has real detents that you can feel and hear.
So yeah, looking at haptic feedback, we have also categorized it into 3 categories a little bit. So you have the contact haptics, you know that from the keyboard, and that is also not just for fun, but it's really helpful because your user is probably not going to look at the keyboard during typing. So the haptic feedback gives them some sort of confirmation that what they're doing is successful. The same thing applies to confirmation haptics. This, like, it might be hard to see, but what we're talking about is the silence mode pop-up at the top. If you do that in your pocket, you're not even looking at your screen. And if you're switching your phone to silent, you also don't want to hear a sound because you want it to be silent. So the haptic feedback is really helpful here to let the user know that their action has been successful. And then the example at the end, also, we call it continuity haptics here, but what it's for is basically letting the user know, first of all, how to interact with the element because it reminds them of a real physical object. But then again, also, if they are scrolling for a long time, they have an intuitive sense for how many numbers they skipped in this case, which can be really helpful. And if you want to build that yourself, there's Flutter APIs for this that you probably know, easy to Google also. But one thing we wanted to shout out is there's a thing called Meta Haptic Studio. And you can basically design your own haptic sequences with it also if you want from an audio file that you put in, and then export it to a few formats and build it into your app. And that is how you would create something like the Formula 1 haptic trailer that Apple released earlier this year. I don't know if anyone saw it, but you can create something like this or just longer, more complicated sequences.
All right, so the next part is motion, and I think this is a really interesting part for physicality. What we have here on the left side is a super simple application. It has one button, and if we press the button, we open a bottom sheet. But we see that something is broken here, and it's obvious the animation is missing. So without this transition, the whole thing feels jarring and unnatural. We can see this even more obvious if we activate our motion graph, and you can see it's a perfect rectangular shape. So the bottom sheet really pops into existence out of nowhere. So how can we fix this?
Pretty simple. I think all of you know, we just add motion, and this happens instead. And we can already see this is way better than what we had before, because first of all, the user knows they're in a new context. If you compare this to the slide before, in this case, it might look like this button jumped down at first. You don't see that it's a different button immediately. But with the motion, it is immediately clear, okay, this is a new context. Also, the user sort of knows where this came from, so this might give them the hint what to do to get it to go away again. In this case, they can just swipe down. But this is still not perfect. It feels a little bit off. And it's very easy to see why if we activate this graph again. You can see there's a very abrupt stop and a very abrupt start because we are just animating the motion linearly. So you have these peaks and valleys here that are strong kinks. And that is also something that in the real world, it doesn't happen. Every element you interact with in your life has a mass. So if it just starts moving abruptly and it stops moving, your brain thinks there's either no mass at all or an infinite force. And that is not accurate. So it feels a little bit jarring. What can we do to fix that?
So come on, Tim, this is easy. We all know it. Add a curve. All right, this is way better already, right? Now we have some easing added and the movement is way more fluent. And if we check the graph again, we can also see it. The kinks are gone and we have a smooth slope and movement of our sheet.
But one thing that can go wrong here, and you might not know this, but if you start looking for it, you see it in a lot of apps, is that on the way back, people often use the curve the wrong way around. So we have the same easing curve here that we had just now, but now on the way down, we forgot to flip it. So while the sheet moves up and decelerates slowly, on the way down, it suddenly takes very long to accelerate. And that is, again, very confusing for your brain because it feels like the sheet changed mass, and it doesn't really make sense. And another thing that is not optimal about using curves for this is that if we let the user drag our sheet again and they throw it down, it does this. I don't know if you can see this well, but if you feel it, you really notice. And we just look at the graph again to show you. So if I move this sheet around and now I fling it down with velocity, it has this kink again. So we're back to square one. The motion stops for a second, and just imagine throwing a ball somewhere and it stops in the air for a second and then starts moving slowly. It just feels weird. Why would you do it?
All right, so how can we solve that? And there is something called spring simulation. So let's first check the app again. So that movement feels still natural. It's pretty similar to the curves actually, but can you now swipe it down? Wow, it still works perfectly. There is no kink whatsoever. So this works because a simulation is simulated every frame and we can take into account the user's initial parameters.
So let's talk about for a second how you can conceptualize a spring simulation. And it's actually pretty easy. So we have this visualization here, and the red circle means our target for where we want to animate, and the blue circle represents our current animation value. And if I now move the target, we can see that we're basically putting a spring between our target and our value, and then once we start the animation, the spring starts pulling in this object. And we have a bunch of ways we can configure this, but the interesting point here is that since this simulation is run on every frame, we can also start moving the object around in real time, and the target will always follow and always behave in a physically correct way.
All right, and we can use those spring descriptions to define different motion characters. So there is the smooth animation we know from iOS. There is a more playful animation where we add a little bounce. There is the snappy animation you might use if you want to be not so intrusive to the user, but still communicate the context. And there is one thing where you have to be a bit careful. You can technically misconfigure a spring, or maybe you have a use case for that, and I didn't find it. But it is possible that a spring springs forever. So be careful. So how would we do this in Flutter? So basically, it's pretty basic physics. The normal spring constructor takes a mass, a stiffness, and a damping. More mass makes you slower, more stiffness makes you faster, and damping works kind of like friction. Higher damping means less bounce. And since this constructor is a little bit hard to predict. So if I set the values, I don't know how the movement looks like. But now Flutter has a better constructor where you set a duration and a bounce factor. One thing you need to keep in mind is that this duration is just an approximation, because depending on the initial values of your simulation, it might take longer or shorter to settle. How would we use this now? For example, in our bottom sheet, we have an animation controller, and when the user lets the sheet go on drag end, we need now to use the velocity of the drag in order to parameterize our spring simulation. And the spring simulation takes the spring description, an initial value and a target value, and the user's velocity, and then it animates away. So I think with that in mind, we never use curves again. Springs are the way to go.
It's not quite that simple, and it gets complicated real fast. So let's look at another interface example. And here we have a classical drag and drop interface. So the user can take a file and drop it onto a folder. But since we want to build good UX, we also want to let the user know when they missed the target and we didn't actually perform the action that they wanted to do. And in this case, we decided to just animate the object back to its original position. Makes sense, right? The user understands, okay, nothing happened, it's back where it started. But if I start moving this around again, even though we use a spring simulation for this, like we just talked about, and drive an offset tween with that simulation, it still feels off. And we're going to graph this again so you can see it better. If I move this and let go here at this point, it suddenly does this weird turn again and just moves back in a straight line. Why doesn't it keep the velocity that I gave it?
All right, let's first think about how we want the solution to work. And actually you can see it here. You can see it even better with the graph. So what we want is a smooth movement across both dimensions to animate back to its origin point. And we can implement this in Flutter. We just need to use two animation controllers, one for each dimension of the movement. And for a 2D drag interaction, that actually still works kind of well, right? It's not too much hassle. But if you think about more complex animations, the next one could be, for example, paddings. And then you already have 4 values. So we already get the feeling the whole thing is not really scaling well.
So to conclude, let's summarize a bit. Are physics simulations just better? There's a few very good parts about them. They are highly dynamic, and that makes them perfect for any animation that is driven directly by user input, what we just saw. And you can't really use them incorrectly in the sense that you cannot build a non-physical motion with them. While like if you use the curve the wrong way around, you might have the bounce on the wrong end, and then you build an animation that is not physical. That can't happen with a spring simulation. The bad parts are it requires multi-dimensional simulation to get a few things right, and that can be a little bit cumbersome in Flutter. Just imagine having 4 animation controllers. You need to remember to dispose all of them, and it's not that easy. And also what Jesper just mentioned, the duration is never guaranteed, so you can never just rely on the animation ending at the exact timing for spring simulations. The ugly parts are configuring can be unpredictable. So if you, for example, look at the bounce factor we just talked about, and you decide to bind that to a user input value, and you end up with a high bounce value, suddenly your animation just never stops or bounces out of your screen or something. So that you need to be mindful of. And if you're an engineer, the handoff with your designer can be a little bit trickier, because a lot of design tools don't have this concept of real-time physics simulation. So your designer might have prepared this perfect animation for you that is based on an easing curve, and then they want to hand that over, and you need to explain to them what the physics simulation would do, and it is maybe not as predictable. Good news, we think the bad parts are fixable. So for the last 10-ish minutes, we want to talk to you about a package that we built to make all of this easier for you, and it's called Motor. And we also have links at the end. And let's start with the basic concepts of this package. And the first thing we want to talk about is a class called Motion, and that is basically just a unified abstraction for both curves with durations, as we can see here, as well as spring simulations. And we also offer a few tokens that we took from SwiftUI, so you can build motions that feel like the real thing on Apple platforms. You can also modify your motion with certain extensions that not super important for now. And Material Expressive also changed their entire motion system to Spring simulations, and Flutter doesn't support it yet. So if you import Motor, you also get access to that.
Is that me? Okay.
Sure.
No, it's you.
Okay, sorry. Yeah, no, the second concept is something called motion converter, and that is basically what you might use a tween for now. So what a motion converter does is it gives Motor the understanding of different types and which dimensions they need to be simulated with. So we include common types like a single value or an offset or an alignment. But if you, for example, have a state of your button and you want to animate the radius, the opacity, and the elevation, you can provide your own custom motion converter. And all you need to do basically is to normalize your value into a list of doubles and denormalize it from a list of doubles. And then we basically know how many dimensions we need to simulate and in what way we simulate them.
All right, so let's visit our example from before again. So we again have a drag target which should return to its origin whenever the user lets go. And we implement this now with the motion controller, and the motion controller is of type offset. So this is the type we want to animate. Therefore, we also need to add the offset motion converter in order to tell the system that it now needs to animate an offset. We use a specific motion, and we have our initial value here. So let's take a look what happens when the drag is ending. Let's look first up how we update, because this is also nice. Now that we have the converter already built in, we can directly take the update from the on-drag update and feed it as a value back to the controller. So there is no conversion necessary anymore. And on drag end, it is pretty much the same code as before. We say again, okay, we want to animate to a specific target, offset 0 in this case, and then we hand over again a initial parameter, and this is again in this case the velocity of the drag. And if you are lazy as I am, you might like declarative animations more, where you basically just have a state and the UI should figure out how to get there. I don't want to make it manually. And then you can use a motion builder, which basically abstracts the motion controller for you. And in this example, you can see we just swap out the alignment value. And if we do it really fast, we see that the animation never breaks, no matter how fast we do it, because it's a simulation. So always when we switch the target, we take over the velocity of the last movement, and it always stays smooth.
And now, towards the end, we want to talk about one more a bit advanced concept. I don't know how much time we have to get into detail, but I'll try to make it quick. So let's say we want to build this stack of cards, and you might know this from dating apps if you're on them. The user is supposed to swipe cards away. So I can swipe these cards away, and they fly to the back of the stack in this case. But we don't want the card to just pass through the stack. So we need to make sure that wherever I let it go, it moves out first to clear the stack, and then it can sort itself behind it. And I ideally want to do that in a physical manner, no matter with which velocity I fling the card, and it should always feel natural. And for that, we have something in Motor called a motion sequence. And I'm just going to go through it really high level. If you're interested, you can check out our README. But in this case, the card has 3 phases. It has an idle phase, where it is just no motion at the current offset. And then if we let go, we enter a clearing phase. And in that clearing phase, we basically first calculated the offset that the card needs to have to move past the stack. And we animate there with a smooth spring that we cut really short. And that is a bit difficult to explain conceptually, but why we want to do this, if we use the whole spring simulation, the card would basically move out, stop here, Motor would wait until the simulation is finished, and then it would move back. By cutting the motion, we're basically ensuring that the card changes direction. It moves all the way to the point we define still, but it changes direction sooner, and it still has some velocity. And then, if we enter the last phase, that is called dismissing, we just go back to offset 0 with a smooth spring. And there we want to use the full spring, obviously, because we want the velocity to return to 0 smoothly when it returns. And then what we can do basically is we instantiate a controller again. I'll skip through that. And we can call play sequence on that controller, and it will automatically progress through this sequence. And that is nice for a gesture-driven animation like this, but it's also just really convenient if you want to make a fancy onboarding animation and you just want a bunch of states that play from A to B in the second and then half a second for the next state. You can just chain them very easily with this sequence concept. And this is all really powerful, and these are just our last few demos. There's another package we maintain. It's called Heroine, as in female hero. It's basically the concept of hero transitions from Flutter, just simulated by physics. So you can see that if I open this card and I can close it with a drag, it also follows the smooth natural parts and other smooth natural arcs, sorry. And other than that, it just works like your normal hero. And then another example that we wanted to show off real quick is we built this entirely custom page view that is also built in Motor, and it also offers physical spring motion, and this is 300 lines of code. And the card stack example is actually 200 lines of code. So overall, this just enables you to do these complex simulations in really terse code. Thank you.
Thank you.